and evolved. The Earth's first atmosphere was probably composed mostly of nitrogen, like it is today, with a little bit of carbon dioxide. Oxygen, the stuff that we breathe, that we need in the air, actually didn't start accumulating until a couple billion years ago. Now, of course, Venus, I mentioned, has all that carbon dioxide in the atmosphere. It's super greenhouse. Earth has a lot of carbon, about the same amount of carbon as Venus has. But where Venus invested its carbon in the atmosphere to create a super greenhouse, Earth has locked up most of its carbon in limestone. And we'll talk about that a little bit later. But what that means is that the greenhouse effect is much, much weaker here on Earth. But we still have a natural greenhouse. The sun shines on the Earth, the light streams down through a transparent atmosphere, but greenhouse gases in that atmosphere that allow that sunlight to come down through stop the heat from radiating back out into space. They're transparent to the incoming sunlight, but opaque to the radiated heat. Here on the Earth, those greenhouse gases under normal conditions raise the Earth's temperature by about 58 degrees. In other words, without a natural greenhouse effect, without that carbon dioxide in the Earth's atmosphere, it would be freezing, literally, all over the world. So, those greenhouse gases that are so important to us, we always hear about carbon dioxide. It's the one in the news. But there are a number of gases in the Earth's atmosphere that do act as a greenhouse. Carbon dioxide is actually one of the weaker ones. And this chart here shows you how they vary. The three most important greenhouse gases, carbon dioxide, methane, and nitrous oxide. They vary, with carbon dioxide being the weakest, methane being over 10 times, about 30 times stronger greenhouse gas than carbon dioxide, and nitrous oxide being about 10 times stronger than that. You'll notice that the units that this is measured in are watts per meter squared per part per billion. So keep that in mind. No, don't keep that in mind. Just remember that even though carbon dioxide is not the most powerful greenhouse gas, it's the most abundant greenhouse gas. So that's why it gets all the press. Water vapor is another greenhouse gas. In fact, of that 58 degrees of warming that we get from our planetary greenhouse, about 2/3 of that comes from water vapor in the atmosphere. So water vapor is important in holding the warmth of the Earth here, but it doesn't drive temperatures. Water, if the temperature goes up, water evaporates. If the temperature goes down, water condenses and falls out of the air as rain and snow. So although the water vapor in the atmosphere traps warmth on the Earth, it does not drive our planetary greenhouse. Instead, it responds to our planetary greenhouse. And we'll take a look at some of those responses later on tonight. So if carbon dioxide, albeit a rather weak but plentiful greenhouse gas, is so important, what's it doing? Well, you know, when we were all in school, we all learned about the carbon cycle. You know, the plants grow in the sun, the plants soak up the carbon dioxide to make sugar, the animals eat the plants, get the sugar out, the animals burn the sugar and release the carbon dioxide back into the atmosphere, consuming oxygen in the process. So it makes this nice cycle from plants to animals, back to plants, back to animals. And that's what we call the organic carbon cycle. Organic because it's the plants and animals that are doing the cycling. There's also another carbon cycle. It's the long-term or geochemical carbon cycle. And in terms of the Earth's climate, it's actually more important. The geochemical cycle, the carbon dioxide winds up being stored in rocks, primarily in limestone and dolomite, what we call carbonate minerals. Get it? Carbonate, carbon, carbonate, there's a connection. So, carbonate minerals store most of the Earth's carbon. There's less in fossil materials like coal, natural gas, oil, things like that. That does store some of the carbon in the geochemical cycle, but most of it is stored in limestone. So when those rocks form, they lock up carbon dioxide, and when those rocks are weathered or erupt out of a volcano, or in the case of some of the things like coal or oil, are burned, it returns that carbon dioxide to the atmosphere. So, as you can imagine, this geochemical cycle is much slower than the organic cycle. The organic cycle cycles every year, up and down. As spring turns into summer, turns into fall, turns into winter, into spring, into summer, into fall, into winter. The carbon in the atmosphere follows that. The geochemical cycle is more tightly attuned to things like continental drift. You know, continents moving along about as fast as your thumbnail grows. A very slow, ponderous cycle, but cycling most of the carbon in the Earth's system. So, what do we find, knowing these things about air, what do we find if we look at rocks and air? Well now, all along, you probably noticed this little cross-section of the Grand Canyon over here in the corner, and you probably thought it was a decoration that I put on my slides. Actually, it is, but it's also a cross-section of the Grand Canyon because as we talk about the history of the Grand Canyon area and what it can teach us about the climate, we're going to be moving through these rock layers. And now, I'll tell you right now, I know the names of all these rock layers, but I bet that there are at least 3 people here who couldn't recite all of these in order with proper spelling. And so what I did was I put this slide up here so you could memorize it all real quick. Is everybody done? Okay, good. These are the rock layers of the Grand Canyon, starting from our very oldest rocks in what we call the Vishnu basement, the stuff that is 1.84 billion years old. Really old stuff, not even half the age of the Earth, but it's the oldest we got at Grand Canyon. Running through a set of rocks that we call the supergroup that was formed roughly 1 billion years ago. And then the rocks that form the layer cake that's so familiar to us when we look at the Grand Canyon. Now, at this point, hopefully not too many of you are looking at your watches yet. But if you want to keep track of where we are in the presentation, over here on the far right, you'll see little arrows and brackets appear and disappear in this. And this is to let you know where we are in this rock column as we start talking about what these different layers can tell us about the history of the canyon. So when you start to get a little bit confused, just take a look over here and all will become clear. At least I hope a little bit will become clear. So, early on, I mentioned that the Earth started out with virtually no oxygen in its atmosphere. Today, oxygen is almost 1/4 of our atmosphere. That oxygen only has been around for about the last half of the Earth's history. For the first half of the Earth's history, there was no oxygen in the air. Oxygen started accumulating about the time that certain bacteria learned how to use sunlight to make sugar and release oxygen as a toxic waste product from that chemical reaction. The first oxygen that was released by those nasty little polluters actually went into rusting iron. And we find deposits of banded iron all over the world. But they're much older than our rocks here at the Grand Canyon. Those banded iron deposits, though, did soak up a lot of oxygen, but eventually the iron was gone. And so free oxygen started to circulate in the seawater. And the Earth probably went through a tremendous mass extinction as this toxic, reactive oxygen started poisoning everything in sight. Tremendous extinctions, but everybody that was becoming extinct was one cell, maybe, like a micron and a half long. They were bacteria. And who cares if bacteria become extinct? So we don't often hear about this very huge extinction that happened 2 billion years ago. And in fact, we really don't know a whole lot about it because those fossils are so hard to come by. But once oxygen was in the atmosphere, life adapted. Life learned how to live with oxygen. And in fact, in our case, learned to require oxygen. We can't live without it. And so consequently, we're quite fortunate that the oxygen has been maintained in our atmosphere, mostly by photosynthesis, mostly by our friendly neighborhood plants and photosynthetic bacteria. And they've been doing it since well over 1 billion years ago. Our oldest fossils in the Grand Canyon are from photosynthetic algae that were growing in some of the shallow seas there at the Grand Canyon. As those creatures were producing oxygen, they were consuming carbon dioxide, and some of